Let us now discuss shear force and bending moment diagrams using an example. Before we take an example, let us try to understand what shear force and bending moment diagrams are. Shear force and bending moment diagrams are graphical representations of shear force and bending moment distribution within the structural elements. These diagrams visually represent the flow of external forces within structural elements. They give clear idea of how external forces get transmitted to the supports through the structure. Shear force and bending moment diagrams are essential to structural design, as they give occurrences and locations of maximum shear forces and bending moments within the structural elements. These maxima and minima are used to determine cross-sectional requirements for the structural elements given the type of material used. Stresses are calculated from these values and cross-sectional area is adjusted to meet the permissible stress values after applying safety factors. Let us now take an example on shear force and bending moment diagrams. As you can see, we have a beam of total of 8 meter length. The support conditions are hinge or pin at the left end, which is point A, and roller at the right end, which is point B. The beam is subjected to a uniformly distributed load of 5 kilonewtons per meter over a span of 4 meters between point A and C, and a concentrated load of 5 kilonewtons at 2 meters from the roller support, which is point D. The first step to plotting shear force and bending moment diagram is to find out support reactions. For calculating support reactions, you need to first sketch the free body diagram. What is a free body diagram? It is the visual representation of the structural element or component in hand, free from the supports or surroundings, taking into account the reactions offered by supports and the external loads. The reactions at this point may or may not be known to us. The free body diagram converts the structural model to the analytical model. As you see over here, we have a hinge support that offers two reactions, a horizontal reaction and a vertical reaction, and a roller support that offers only vertical reaction. For developing the free body diagram, we have removed the supports from the structural diagram and rather have represented them with their reactions instead. The external forces remain as they are. We usually represent support reactions using the letters for directions and subscripts denoting point at which they act. Hence, as you can see, we have HA and VA for horizontal and vertical reactions acting at point A, and VB for vertical reaction acting at point B. Having discussed the free body diagram, let us now determine the support reactions. The supports offer reactions in order to balance the external loads. Obviously, it is understood that the supports are strong enough to withstand external loads coming from the structure. In order to determine the reactions, we need to use conditions of static equilibrium. We'll have to formulate equations pertaining to each condition of static equilibrium. As this is a two-dimensional problem, there are three equations of static equilibrium that we can use. Namely, horizontal equilibrium equation represented with summation of all the forces acting in x direction reducing to zero, vertical equilibrium equation represented with summation of all the forces acting in y direction reducing to zero, and rotational equilibrium equation represented with summation of all the moments taken about a point reducing to zero. In order for this beam to be in equilibrium, the actions, that is the external forces, and reactions must nullify one another. This means that the sum of forces, both actions and reactions at a point, which means locally or globally, must be zero. In short, we can say that in general, the body is in equilibrium if and only if all the forces acting in horizontal direction sum up to 0, all the forces acting in vertical direction sum up to 0, and that the body is not rotating. So now we can formulate the equations of static equilibrium. We can represent summation by Greek alphabet sigma. Our first condition of static equilibrium is sigma fx equals 0. This talks about the horizontal equilibrium of the beam. As you can see, there are no horizontal forces acting on the beam. The horizontal reaction offered by the hinge support does not have to balance anything. If we had to write the equilibrium equation in the horizontal direction, we could have written something like HA plus or minus any external forces equal to 0. In the absence of any external forces, HA is not triggered at all, hence HA is 0. Coming to the vertical equilibrium equation, that is sigma Fy equals 0. We can clearly see that we have two reactions, VA and VB, acting upwards, and two external loads, 5 kilonewtons per meter UDL and a 5 kilonewtons concentrated load acting downwards. VA and VB have to balance the external loads coming on the beam, so that we can write something like VA plus VB, that is acting upward, equals 5 into 4, that's the total load represented with UDL, and 5 kilonewton, that's the concentrated load, totaling to 25. Hence, VA plus VB equals 25. Our third condition of static equilibrium is sigma mz equals 0, which represents rotational equilibrium. We can take moment about any point on the beam, depending on what reaction we want to find out first. We'll take moment about B. Let us say we want to find out reaction VA first. Looking at the equation for the moment, there are three parts to it. VA into 8 represents moment of VA about point B. The second term, 5 into 4 into 2 plus 2 plus 2, represents moment of UDL about point B. And the last term, 5 into 2, represents moment of concentrated load about point B. A moment is the product of the force multiplied by the perpendicular distance between the point and the line of action of force. You can see that VA is 8 meters away from point B. Hence, the first term VA into 8 represents moment of force VA about point B. The second term, 5 into 4, represents total load or total magnitude of the UDL. The intensity of the UDL is 5 kilonewtons and it is distributed on 4 meters. So the total load is 5 into 4, that is 20 kilonewtons. It can be easily understood that the total load 5 into 4, that's 20 kilonewtons, it is acting at the CG of the uniformly distributed load. The CG of this uniformly distributed load is exactly at the midpoint, which is 2 meters away from point C. Hence, the total perpendicular distance between the line of action of the total UDL, that is 20 kilonewtons, and point B is 6 meters. Lastly, we have our concentrated load as 5 kilonewtons, which is 2 meters away from point B. Hence, the moment is 5 into 2. Simplifying it, we can easily find out VA. VA, as a result, turns out to be 16.25 kilonewtons. Substituting VA into equation generated by the vertical equilibrium condition sigma Fy equals 0, we can easily find out VB, which turns out to be 8.75 kilonewtons. Here is an alternate method for finding out reactions. This method comes handy when the loads acting on the beam are within the span supported by supports and when there are no loads acting on the overhangs, if there are any. For this method to work, we'll need to convert all the distributed loads to their equivalent concentrated loads acting at the CG of the respective distributed load. The CG for a uniformly distributed load, for example, is at midpoint of the length of the UDL. That for a uniformly varying load with zero intensity at one end is at distance equal to 2/3 of length of the distributed load measured from the point of zero intensity. Here in our example, we have two loads acting on the beam, a uniformly distributed load of 5 kilonewtons per meter spread over 4 meters of span and a concentrated load of 5 kilonewtons acting at 2 meters from point B, which is a support. We need to convert this distributed load to its equivalent concentrated load, which can be easily done by multiplying the intensity of the uniformly distributed load with the span on which it is acting. In our case, we'll be getting 5 multiplied by 4 is 20 kilonewtons. And after converting to its equivalent concentrated load, it should be placed exactly at the CG of the uniformly distributed load. As the length of the uniformly distributed load is 4 meters, the CG of the uniformly distributed load is exactly at midpoint, which comes out to be 2 meters. Hence, we have placed the 20 kilonewton load at 2 meters from support A. Now that we have converted our uniformly distributed load to its equivalent concentrated load, let us try to understand how a load gets shared amongst the supports. You can intuitively think that any load gets shared amongst the supports in proportions of the span in which it divides the whole beam. For example, this load P divides the whole beam in two spans, namely A and B, so that the total length of the beam L becomes A plus B. You can also see here that load P is closer to support B, which means that VB will be more in magnitude than VA. So that we can write VA is equal to P into B over L. B over L over here determines the proportion by which the load gets shared to VA. Similarly, VB is P into A over L. This is nothing but the extension of the moment equations. You can easily arrive at this equations by taking moments at each point. But it is very intuitive to think in this way. Now we can use the principle of superposition. We can take the contribution of each load and find out the reaction only for that load and sum up all the reactions in order to get the total reaction. For example, over here, our total reaction VA is VA due to the uniformly distributed load and VA due to the concentrated load. So we can write 20 into 6 over 8. 6 is 2 plus 2 plus 2, that is our B, and A is 2 meters. So P into B over L, that becomes 20 into 6 over 8. And that for the concentrated load is 5 into 2 over 8, that is 16.25 kilonewtons. Similarly, VB is VB due to UDL plus VB due to concentrated load, and we get 8.75 kilonewtons, which is exactly same as what we have calculated in our previous method. Note here that because we had only two loads coming on the beam, we had two terms representing contributions from each load. If we had more than two loads, we would have added more terms representing the contribution from each load in order to get the total reaction. Now that we have determined the reactions, let us calculate shear force and bending moment in the beam. Before we dive in, we need to understand the sign convention. The way that shear force and bending moments are calculated within the beam is that we take an imaginary section that passes within the span of the beam. We can go from left to right or right to left. During the passage of the section from left to right, any forces going upwards will be considered positive and will be plotted on the top of the baseline. On the other hand, going from right to left, any forces going downwards will be considered positive. In case of bending moments, any moments in the clockwise direction going from left to right will be considered positive. Conversely, going from right to left, any moments going in anti-clockwise direction will be considered positive. Now that we have understood the sign conventions, let us now try to understand how the values for shear force and bending moment diagrams are calculated within the beam. For this example, we will go from left to right, meaning that our section will start at left of support A and will end at right of support B. Before we do that, we'll have to mark the important points on the beam. Our supports are marked by point A and point B. The point at which this UDL end is point C. The point at which the concentrated load of 5 kilonewtons is acting is point D. We will place our section between these critical points. We will generate the mathematical expression for both shear force and bending moment, and then we will calculate the values at each critical point. We'll join the values by the curves represented by mathematical expressions generated within each segment. We'll measure the distance of the section from the left end. Let us now start by placing our imaginary section between points A and C, which form our first segment of the beam. Notice that the distance of the section is measured from support A. As you can see, we have sketched the free body diagrams for portions to the left and right of the section. We will, however, consider only the free body diagram for the portion to the left of the section as we are going from left to right. We have denoted our shear force as Sx and the bending moment as Mx. Notice that the subscript x represents value for shear force and bending moment at the section. Considering the free body diagram to the left and applying the equations of equilibrium, we can see that we have forces acting only in y direction. Following the sign convention, going from left to right, any forces going upwards are considered positive. Hence, 16.25, which is the reaction, is considered positive. The UDL, or you can say the partial UDL, acting on the length of x meters, is going downwards. The total value of that UDL is 5 into x, and because it's going downward, it is considered negative. So the final expression for shear force becomes 16.25 minus 5x. Coming to the bending moment equation, you can see that the bending moment, or you can say the moment of reaction VA at section X is 16.25 into X. 16.25 for the magnitude of the force and distance X from the support to the section. Coming to the UDL, as you can see, the total value of the UDL is 5 into X, and considering its equivalent concentrated load, which is acting at the CG of the partial UDL, the lever arm becomes X by 2. So the moment of the uniformly distributed load about the point on a beam at section X becomes 5 into X by 2. So the final expression for bending moment becomes 16.25x minus 5x squared over 2. Please note that these expressions of shear force and bending moment are valid for the values of x between 0 and 4 meters. Please also note that for shear force, this expression is left bound, meaning that any forces acting at 4 meters is not reflected in this expression. In order to have the effect of that force, you'll have to consider the shear force expression for the next segment. For bending moment, this does not apply, as we calculate bending moment at a point. Going forward with the example, let us place our section between points C and D. Generating the expression for shear force, we get 16.25 minus 5 into 4. 16.25 is the reaction going upwards, hence considered positive, and the uniformly distributed load spread on 4 meters is going downwards, hence considered negative. The final expression for our shear force becomes 16.25 minus 5 into 4 equal to minus 3.75 kilonewtons. Notice that there is no x term in this expression, meaning that there is no variation in the shear force. It means that the shear force between points C and D will remain constant with a negative value, hence will be plotted below the baseline. Coming to the moment equation, we can see that the moment due to the reaction is 16.25 into x. That for the uniformly distributed load about the point on the beam at the section is 5 into 4 into x minus 2. 5 into 4 is the total distributed load, and the CG of that load is exactly at 2 meters from support A. The distance of the section from support is measured as x. So the line of action of the equivalent concentrated load is passing exactly at x minus 2 from the section. Hence, our final expression for moment becomes minus 3.75x plus 40. Notice that over here the variation of shear force is constant, whereas the variation for bending moment is linear, having negative slope. Finally, let us place our section between points D and B, which is our last segment. Over here, you can go from right to left, as there will be fewer forces to handle. But for the sake of uniformity, we'll still go from left to right, and we'll still measure our x from left support, that is support A. Forming the equation for shear force, we can clearly see that we have 16.25 going upwards, hence considered positive. 5 into 4 as uniformly distributed load, that is going downwards, hence considered negative. And a concentrated load of 5 kilonewtons, that is going downwards, hence considered negative, giving us the final value of negative 8.75 kilonewtons. Coming to the moment equation, we have a moment due to reaction VA as 16.25 into x, that due to the uniformly distributed load as 5 into 4 into x minus 2. Notice here that this x minus 2 is the distance between the section and the CG of the uniformly distributed load. The last part of the moment is due to the concentrated load, that is negative 5 into x minus 6. The total distance between the section and support A is x. Deducting 4 plus 2, 6 becomes x minus 6. So our final expression for bending moment becomes negative 8.75x plus 70. It will be quite convenient for us if we list all the expressions for shear force and bending moments for different sections and construct tables listing values. It will be super easy for us then to plot shear force and bending moment diagrams referring to these tables. As you can see over here, I've listed all the 3 expressions for shear force valid for different segments. I've also constructed a table for shear force. It has 3 columns, namely segment, point, and shear. The segment column lists all the segments with their effective spans. The second column lists all the points with left and right demarcation. And the shear column lists all the values. Let us focus on the first expression. This expression of shear force is valid for segment AC for the values of x between 0 and 4. Notice here that this expression has a degree of 1. It means that the maximum power of the variable x in this expression is 1. When plotted in 2-dimensional space, it will trace a line. Notice also that this line is having the negative slope of 5. Let us now substitute the values of x in each of these expressions. Focusing on the first expression where our x is ranging from 0 to 4, we can see that on the left of A, because the beam doesn't exist there, the value of shear is 0. Just to the right of A, x equals 0. Putting x equals 0 there, you get 16.25. Putting x equals 4, we get negative 3.75, which is just to the left of point C. Any loads acting at point C are not considered in this expression. That load will be considered in the expression for the next segment. That is how the shear force values are calculated. Going to the next expression, you can see here that the value for shear force in this segment remains constant as there are no x terms. The value of shear force in this segment is negative 3.75, which means that it will be plotted below the baseline. The variation of shear force from point A to C is linear. So the values of 16.25 and negative 3.75 will be joined with a line. Coming to the second segment, CD, the expression for shear force in this segment is 16.25 minus 5 into 4, giving us the constant value of negative 3.75. As there are no any x terms, the variation of shear force is constant. It is having a negative sign in front of it. It means that the value of the shear force is plotted below the baseline. This shear force remains constant between point C and D, just to the left of point D. Similarly, going to the third expression, given by Sx dB equals 16.25 minus 5 into 4 minus 5, it gives us the value of negative 8.75 kilonewton. The value of the shear force in this segment is again constant with a negative sign in front of it, which means that it will be plotted below the baseline. The value of negative 8.75 remains constant till just to the left of point B. Let us now plot shear force diagram and bending moment diagram based on these values. We'll refer each table and the corresponding diagram. We'll start with the shear force diagram. As you can see over here, we have a value of 0 on the left of point A. In our diagram, we don't have a beam on the left of point A, hence the value is 0 there. It's not plotted at all. As we cross point A, we have a reaction having a magnitude of 16.25 kilonewton. Looking at the shear force table, when we are just to the right of point A, we have a value of 16.25 kilonewtons. Hence, the value of 16.25 kilonewtons is plotted on the positive side of the baseline. Going to the point C, we have the shear force value as negative 3.75 kilonewtons. Notice here that this variation is linear. As we enter the next segment, that is between point C and D, referring to the table, we can see here that this variation remains constant as there are no loads in this segment. Hence, we have a straight line denoting the constant nature of the shear force within this segment. As we cross point D, negative 5 kilonewton gets added to that expression and we get minus 3.75 minus 5, giving us the new value of negative 8.75, which is evident from the table. Again, in this segment, the variation of shear force is constant. Hence, we have a straight line with zero slope. As you cross point B, when you are just on the right of point B, a reaction of VB gets added and it reduces the shear force expression to 0. This closes the shear force diagram. Before we move on to the bending moment diagram, we have a point to discuss over here. Notice here that the shear force changes its sign from positive to negative at some point between points A and C. In structural analysis, in structural mechanics, the variation of shear force and bending moments are interrelated. Bending moments takes its peak when the shear force is 0. We need to calculate the maximum value of the bending moment at this point. The value of the bending moment is maximum when shear force is 0. We'll have to locate this point. As you can see over here in our bending moment table, we don't have a maximum value. We have calculated the values of bending moment at critical points. The maximum bending moment occurs somewhere in between points A and C. We have our shear force reducing to 0 somewhere between points A and C. We'll need to locate this point and calculate the bending moment accordingly. But before that, let us now plot the other values of bending moment. Referring to the table, we have our bending moment for segment AC. At point A, we have a 0 bending moment. At point C, we have a value of 25. This variation, according to this expression, is parabolic. That too, parabola opening downwards. But we are not going to plot it as of now because we need to calculate the maximum value of the bending moment that occurs within this segment. For segment CD, we have bending moment of 25 at point C and bending moment of 17.5 at point D, which are plotted here. Again, for segment DB, we have 17.5 at point D and 0 at point B. Let us now locate the point of maximum bending moment and calculate the value of maximum bending moment, which happens at point of 0 shear. Point of 0 shear occurs somewhere in between points A and C. As I mentioned earlier, that bending moment and shear force are related to each other. The change of bending moment with respect to change of span gives us shear force. dm over dx is nothing but the instantaneous slope of bending moment diagram. Maximum bending moment occurs where the slope dm over dx is 0. In other words, the tangent at that point is horizontal. This means that the shear force at point of maximum bending moment is 0. Hence, we will equate the shear force equation to 0 to find out x. The shear force expression in that segment is given by Sxab equals 16.25 minus 5x. Equating this expression to 0 and finding out x, we get x equals 3.25. Making use of the corresponding bending moment equation and substituting the value of x equals 3.25 in that expression, we get maximum bending moment as 26.40 kilonewton meter. Now we can plot the bending moment diagram between points A and C with a peak of 26.40 kilonewton meter occurring at 3.25 meters from support A. Notice that this variation, that's the variation of bending moment between points A and C, is parabolic. This concludes the shear force and bending moment diagram example. Thank you.